Heat spontaneously flows from a hotter to a colder body. In the absence of an opposing external driving energy source, within a body or between bodies, temperature differences decay over time, and thermal equilibrium is approached, temperature becoming more uniform. There are three ways to transfer heat: conduction, convection, and radiation. This video focuses on thermal conduction. Thermal conduction is the transfer of internal energy by microscopic collisions of particles and movement of electrons within a body. The colliding particles, which include molecules, atoms, and electrons, transfer disorganized microscopic kinetic and potential energy when joined, known as internal energy. Conduction takes place in most phases: solid, liquid, and gases. The rate of heat flow through a material can be described by Fourier's law of thermal conduction. In this equation, Q dot stands for the rate of heat flow through a material. The rate of heat flow is the amount of heat that flows per time. Heat is measured in the unit joule and time is measured in the unit seconds. J over S is the same as the unit watt, usually abbreviated to W. This means that this equation gives us the energy flow in watts. The two T in the numerator stand for the temperature. T1 stand for the temperature on one side of the material and T2 stands for the temperature on the other side of the material. Normally the temperature must be measured in Kelvin, but since in this equation we only care about the difference between both temperatures, Celsius can be used with the same result. Which temperature is number 1 and which one is number 2 is not important, we only care about the difference. The X in the denominator stands for the thickness of the material measured in meters. The A stands for the cross-sectional area of the material measured in square meters. The Greek letter lambda is material dependent and stands for the thermal conductivity of a given material. Different materials have different thermal conductivities and therefore allow different rates of heat flow through them. The unit for lambda is watt per meter times Kelvin. The values for lambda can be found in tables that give you the values for all kinds of materials. Now let's have a look at a real-world application. Let's say we have a wall that separates the warm inside of a shelter from the cold outside. This wall has a dimension of 3 meters by 2 meters. The thickness is 0.4 meters. The inside temperature is 20 degrees Celsius and the outside temperature is 10 degrees Celsius. The material is wood. The lambda of wood is approximately 0.15 watt per meter times Kelvin. Putting the numbers into the equation will give us the rate of heat flow through the wall. Now we just plug in the numbers. As stated earlier, whether we use Celsius or Kelvin doesn't really matter, but for the units to work out we have to switch the temperature back to Kelvin. 3 meters times 2 meters gives us a surface area of 6 square meters. The meters cancel each other out. The Kelvin cancel each other out too. This leaves us with the unit watt, exactly as expected. In this example, 22.5 watts of heat flow through the wall. Let's have a quick look at the effect of the different factors in the equation. If we increase the temperature difference, the rate of heat flow increases. If we reduce the temperature difference, the rate of heat flow decreases. If we increase the thickness of the wall, the rate of heat flow decreases, and if we decrease the thickness, the rate of heat flow increases. If we increase the area of the wall, the rate of heat flow increases, and if we decrease the area, the rate of heat flow will also decrease. If we increase the value for lambda by choosing a different material, the rate of heat flow will also increase. If we reduce lambda, the rate of heat flow will also decrease. The thermal conductivity of various materials can differ wildly as shown in these examples. Steel has a lambda of approximately 50 and air only approximately 0.026. This means that if steel was used for the wall instead of wood, the rate of heat flow would be more than 300 times as big. Since the lambda of air is so low, it would be a great material to prevent heat flow. But how can air be used as a thermal insulator? It has to be trapped in some other material depending on the application. Popular methods include trapping air in some kind of polymer foam where the air bubbles cannot move, or use down feathers in clothing to create an air cushion between the body and the outside air. For windows, air can be trapped in between two panes of glass, which improves insulation significantly. Most thermal insulators use some way of trapping air or other gases to reduce heat flow. Thanks for watching. Please like, share, subscribe and hit the bell button for more videos.